Hey everybody, welcome back to Chapter 9. We're moving on to Part 2, continuing our discussion about correlations. Here's a question for you. So, on the left you see a scatter plot, and it's got each of those dots is going to represent one person's score on both their GPA and the hours that they've spent playing video games on average per week. Now, you can see the arrangement of these different dots. And in this particular graph, they've actually fitted a line of best fit through those dots to try to say, okay, this is the line that basically represents the correlation amongst all these different points. And so my question to you is, looking at all these different dots, looking at all these the scatter plot and all these different subjects and their scores on GPA and hours spent playing video games, is this a perfect relationship, an imperfect relationship, or maybe there's no way of knowing? For this, it's going to be an imperfect relationship. You can see actually in the top right-hand corner of that graph that the correlation is negative 0.84. That's a very strong negative correlation, meaning as hours spent playing video games tends to increase, GPA tends to decrease, right? But it's not a perfect relationship. Perfect relationships are either going to be -1 or +1. Anything in between -1 and +1 would be an imperfect relationship, but you can still have differences in strength, right? Like negative 0.84 is still a very strong negative relationship, but it's certainly not perfect. If you were to fit a line of best fit through a perfectly two perfectly related variables, each one of those dots, each one of those subjects or participants, all of those dots would line up exactly on that line of best fit, and that would be perfectly correlation for -1 or for +1 if it was actually going from the bottom left of the graph to the top right. Okay, so you'll remember from last lecture, we were trying to calculate a Pearson's product moment correlation coefficient, also known as just a correlation or correlation coefficient, for these two variables, number of hours studied and the final exam score. And in particular, we had 5 different sets of these scores from 5 different students. So remember last time we actually had to calculate covariance first, and covariance is basically the sum of the deviation products for the x variables and the y variables, where you take everybody's raw score on hours studied minus the mean, everybody's raw score on their final exam score minus the mean exam score. You calculate a product of both the x and y deviation scores. You add them all up, divide by n minus 1, that gives you the covariance, okay? But to find the correlation, the actual correlation coefficient R, you have to divide the covariance by the product of standard deviations for hours studied and exam score. So we did that. We found a final correlation coefficient of positive 0.93. Now that is a very, very strong positive correlation. Remember, the highest a positive correlation could be is 1.00. So 0.93 is very, very strong. But the question remains. Now the question becomes, well, how do we know if and when a correlation is significant? For instance, is a correlation of 0.9 significant? Is a correlation of 0.001 significant? Is a correlation of negative 0.23 significant? And we're going to figure out how do we actually determine whether that's true or not. Well, just like all the other hypothesis testing we've been talking about so far, we need to find some kind of comparison distribution, and that distribution is going to represent the null hypothesis. What is happening if there really is no correlation, there really is no relationship between our two variables. And we're going to have to define some kind of cutoff region or regions, depending on if you're using a one-tailed or a two-tailed hypothesis. And then we look and see, hey, does our correlation that we found fall within the critical region that we establish? And if it does, then we can reject the null hypothesis and conclude that in fact there is a relationship between the two variables. So far, we've talked about, in terms of comparison distributions, as basically being the sampling distribution of sample means, or the distribution of sample means, right? And that is a normally distributed distribution that we can then find different z values for, let's say, a sample mean, and compare it to the mean of the distribution of sample means. And we can say, okay, if our sample mean falls way outside of the original population mean, or the mean of the distribution of means, then we can reject the null hypothesis. Well, for correlations, we don't use a distribution of sample means, because we're talking about correlations, not means. We can use what's called the t distribution. Okay, the t distribution. This is a very important distribution. There are many different t distributions, and basically they all differ depending on how many degrees of freedom are involved. We'll talk about that in just a second. But the t distribution is important here for correlations. It'll also be very important when we move on later in the semester to talk about different kinds of t-tests: one sample t-test, independent sample t-test, paired sample t-test. So you'll see this pop up again and again throughout the semester, so it's important to get a bit of a foundation for it right here. Kind of broadly, the t-distribution is only a little bit different from the standard normal distribution, or like a distribution of z-scores. Okay, so now these t-distributions are going to be made up of t-scores, not z-scores, and t-scores are calculated a bit differently from z-scores. Now, t-distributions, their shape is typically that they have a bit more of their regions in the tails. So they have kind of a thicker tails, or what statisticians literally call fat tails. And so they have more of their distribution found in those tails compared to a standard normal distribution, for example. However, as the sample size increases, the sample size that you're using to create these distributions increases, it actually starts approaching a normal distribution, like a normal distribution of z-scores, for instance. So at first, with very low sample sizes, n, which corresponds to low degrees of freedom, they have thick tails. Okay, but as the degrees of freedom, meaning the number of people in the sample, increases, it starts to approach or approximate a normal distribution. And you can see that here on this image, where with the degrees of freedom of 10, the tails are quite thick. Degrees of freedom of 30, you can see that, okay, more of the distribution is starting to pull towards the middle, towards the mean, because there's a higher peak around the mean. And then with the degrees of freedom of 50, well, now you've got basically a normal distribution there. Okay, so now the t-distribution is going to look just like the standard normal distribution of z-scores. So basically what we're going to get up to is to translate our correlation coefficient R into a t-score, t-statistic, and then compare it on one of these t-distributions to see if it falls in a critical region. If it does, we can reject the null hypothesis and conclude that in fact the two variables that we're interested in are meaningfully, significantly related. And here's how we actually do that, how you translate an R value, a correlation coefficient, into a t-score is you take your correlation coefficient and you multiply it by the square root of the number of people in your sample minus 2. You divide that by the square root of 1 minus your correlation coefficient squared. Okay, so this is just a way to translate or transform our correlation coefficient into a t-score so that then we can compare it to a t-distribution, the comparison distribution, and decide whether or not we can reject the null hypothesis. So if we put our numbers in here, it's going to be that finding a t-score is equivalent to 0.93, it's our correlation coefficient, times the square root of 5, there were 5 total people in our sample, minus 2, divided by the square root of 1 minus 0.93 squared. So go ahead and calculate that for me, and I want to know, what is the t-score? Hopefully you got 4.38 as our t-score. Okay, so we have to compare that t-score of 4.38 to a comparison distribution. The question though is, what were our original hypotheses, and are we testing directional hypotheses or non-directional hypotheses? Our original hypothesis was that there would be a positive relationship, which is a directional hypothesis, meaning it's going to be a one-tailed hypothesis. Although I will tell you that in psychology, typically speaking, when you're talking about correlations, we tend to run two-tailed hypotheses more frequently. So let's go ahead and do both of those things so I can show you how they might be different from each other. So what we need to do is to find the critical value, called the critical value of t, and if the t value that we just calculated, 4.38, if our t value is more extreme than the critical t value that we're about to look up in a table, then that means that our test statistic, our t value, lies in the critical region, which are those regions in blue up there at the top of the image. Those are critical regions. And if our test statistic lies in the critical region, that means that it is a very, very unlikely score. Because remember that the distribution itself on the y-axis is probability density. And so way out on the tails, where those numbers are low, where the curve is very low, less probability of finding something so extreme. So we want to find basically a t-score that falls in the critical region, and that allows us to say, hey, it would be very, very, very weird, very unlikely, low probability of seeing such a extreme t-score. In other words, such an extremely high correlation, 0.93, if in fact the null hypothesis was true. Remember, these distributions represent the null hypothesis, and they say there is no correlation. There's correlation of 0, a relationship, no relation between these two variables. So if we in fact find a very, very extreme t-score on this distribution and it lies in the critical region, we can say, hey, that would be almost impossible or very, very unlikely to see if the null hypothesis was true. Therefore, we can reject the null hypothesis and conclude that the alternative hypothesis is correct. Our alternative hypothesis being that there is a relationship between our studied and final exam score. Okay, so how do we interpret this table? Remember, these values, all those numbers that you're seeing, are critical t-scores. Okay, so that's what we're trying to do. We're trying to establish critical t-scores, which basically help us define critical regions. And then if our t-score is in that critical region, we win. That means we can reject the null hypothesis. Okay, so you can see up at the top that there's differences for one-tailed tests and two-tailed tests. The diagram on the left is for a one-tailed test where we're just interested in one single area of the distribution, and that's what we decided with our alternative hypothesis, was that our two variables are positively related. So we're only going to be looking at basically the right side of the distribution. But you could also have a two-tailed test where you split your alpha, which is your level of significance, which we usually set to be 0.05 in this class. You split it into both of the tails. That's when you use a non-directional hypothesis, just saying, I think that these things are related, but I don't think that they're either, I'm not advancing the idea that they're either positively related or negatively related. I just think they're related in some way. So we're going to go through both examples. So for the first example, okay, you can see that there are different columns that correspond to the level of significance for either a one-tailed test or a two-tailed test. Let's start with the one-tailed test because that's what we actually have been talking about this whole time. We're going to look at the column under the level of significance for one-tailed test that says 0.05 in bold, 0.05. That's because in psychology, we almost always set our level of significance to 0.05, which means 5%. 5%, okay. So we also then, for each of the rows, they correspond to different degrees of freedom. Degrees of freedom, this is important, I would write this down if I was you. Degrees of freedom for correlations is n minus 2. That's how you calculate the degrees of freedom for correlations, n minus 2. Remember, our n was 5 people. There were 5 total people who gave scores. So n minus 2 here is going to be a degrees of freedom of 3. So we basically have to find the row that corresponds to 3, the column that corresponds to a level of significance for a one-tailed test of 0.05, and where those two things meet, that will be our critical value. And you can see that for a one-tailed test, the critical t-value is 2.353 if you have only 3 degrees of freedom. 2.353. Okay, so now we've basically established a comparison distribution, which is a t-distribution, and our cutoff, which defines our critical region on the right-hand side, for an alpha level of 0.05, which is what we're always interested in. The critical t-value is 2.353. That was with 3 degrees of freedom. So if the t-value that we calculated based on our correlation is more extreme than this, then we can reject the null hypothesis because it'll lie in the critical region. Well, let's take a look at that. Well, 4.38 is way more extreme than 2.353, right? So we know without a doubt that the t-value that we calculated based on our original correlation of 0.93 is going to be more extreme than the t-value that we calculated, the critical t-value, meaning that the probability of finding such an extreme t-score, 4.38, probability of finding that is going to be much less than 0.05. Remember, the t-score of 2.353 corresponds to an alpha level of 0.05. Well, we found something way more extreme than that. So the probability is going to be way less than 0.05 that you would ever see such a high relationship, such a high correlation of 0.93, if in fact the null was true, if in fact those two things, study time and exam score, were not at all related. So it's very unlikely that you would see this if they weren't related. Therefore, we can reject that idea that the two variables are not related and conclude that in fact the two variables are related, they're significantly related, and because our alternative hypothesis was in this case that they're positively related, that is also what we have found here. They are positively related. So to sum this up, we reject the null hypothesis that there's no relationship between study time and exam grade, and conclude that there is a significant relationship between those two variables. More specifically, we found that hours of study time and exam score are significantly positively related, such that as one increases, the other tends to increase, or if one decreases, the other also tends to decrease. We found a correlation coefficient of 0.93, and we know that the probability of finding such a high correlation coefficient, given our data, is less than 0.05, meaning there's less than a 5% chance that we would see that high of a correlation just by chance, or that we would see that high of a correlation if in fact there was no true relationship. And we know that it's less than 0.05 because when we translated the R value, the correlation coefficient, to T, we could see that it was way to the right. It was an extreme score, and it was more extreme than the cutoff, the critical value of T for alpha level of 0.05. So if it's more extreme than the chance of 5%, it has to be less than 5% chance of seeing that. Hopefully that makes sense. Let me know if you have any questions about that. Okay, but now let's go back and pretend that we had not created a directional alternative hypothesis, meaning let's say we had a non-directional alternative hypothesis, which means it's going to correspond to a two-tailed test, and the wording would just be something like, I think there is a significant relationship between time studied and exam grade, but I'm not willing to commit to a specific direction. So now what we need to do is we're going to have to change where we're looking at this table, and now we drop down to the level of significance for a two-tailed test in bold. And you can see, again, we're still interested in an alpha level of 0.05. That's going to be our cutoff, alpha level of 0.05. We still have a degrees of freedom of 3 because we still have 5 scores minus 2. N minus 2 is how you find degrees of freedom for a correlation. But now you can see that up in the top right diagram, we've actually split alpha into two different parts of the tail. So now there's only 2.5% of the curve under the left tail and 2.5% of the curve under the right tail, because we split 5%, 0.05, divided by 2 into those two tails. So we're going to have to find basically this is going to define a more extreme critical value of T, because now the tails are thinner way out there. So basically we're going to look at level of significance for the two-tailed test at 0.05, degrees of freedom are 3. So now you can see that the cutoff, or the critical T value that we would have to get a more extreme T value of to reject the null, is now 3.182. Before it was 2.353, but now it's 3.182. So it's actually much harder to find significant results using a two-tailed test. It's harder because the critical value that we have to beat, that we have to get more extreme than, is a higher number. So in this case, 3.182. By the way, that's a positive 3.182 as the t-score on the right part of the graph, but it's defining a negative t-value of negative 3.182 on the left part of the graph. So basically, we have to find a correlation, an R coefficient, that when we translate it into the t-score, is either greater than positive 3.182 or is less than negative 3.182 in order to be in the critical regions and reject the null hypothesis. Okay, so now you can see that we've defined where our new critical regions are, which are way, 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 way out on either end of the distribution, because this is a two-tailed hypothesis. Now in this case, it didn't change anything because we still calculated a t-score of 4.38. That corresponds to our R value, our correlation coefficient of 0.93. So we're still within the critical region, right? We're still above the critical value, more extreme than the critical value of 3.182. So we still lie within the critical region. We still reject the null hypothesis. We still predicted, or we still say that we accept the alternative hypothesis that yes, in fact, there is a significant relationship between hours studied and exam score. However, you can get a sense for the idea that because two-tailed tests split the alpha, the critical regions, in half, basically, and makes it a lot harder to actually find a value that lies in those critical regions, meaning it's more difficult to find significant effects or significant relationships. You could actually have it where a one-tailed test would have found a significant difference between two things or found a significant relationship between two things, but the two-tailed test doesn't, because it establishes more extreme critical values. So in research, oftentimes researchers like to use two-tailed tests because they're more stringent. It means that it's actually harder to find significant results, which means that if you do find significant results, it's more likely that that is accurate, that's a real relationship between those variables. So people don't really like it when you try to use one-tailed tests because it makes it a little easier, actually, that you will find significant results. Of course, if your hypothesis is directional, and you have a good reason for that, given like previous literature in the same area of research, then you can still do it, but it'll raise some eyebrows if you try to do that on a paper. Okay, everybody, that's it for this one. Thanks so much. See you in the next video.